Picture an endless array of realities. In one, you never clicked on this video. In another, your parents never met, so you weren't born. In yet another, the sun never formed from a cold cloud of gas, resulting in no Earth. It might sound strange, but these multiple realities help explain some of the most perplexing aspects of our universe, such as how an electron can exist in two places at once. Our universe is incredibly vast. It contains hundreds of billions, if not trillions, of galaxies, each home to billions or trillions of stars. Some scientists suggest the universe's diameter might be 7 billion light-years across, while others believe it could be infinite. But is there more to it than that? The concept of parallel universes is a favorite in science fiction, where we might be living just one of the countless possible lives. However, this idea isn't confined to fiction. It's a genuine scientific theory that explores the possibility of other universes alongside or similar to our own. Multiverses and parallel worlds are frequently discussed in connection with other major scientific concepts like the Big Bang, string theory, and quantum mechanics. In 1954, a young doctoral candidate at Princeton University, Hugh Everett III, proposed a groundbreaking idea: the existence of parallel universes identical to our own. These universes are interconnected, branching off from one another, including our universe branching off from others. In these parallel universes, often called alternate universes, the outcomes of historical events, like wars, differ from what we know. Species that went extinct in our universe might have thrived and evolved in separate universes. It's even suggested that there might be an infinite number of universes with infinite possibilities. This concept is mind-boggling, yet surprisingly understandable. Ideas of parallel universes resembling our own have appeared in science fiction and have been used to explore metaphysical questions. But why would a young, emerging physicist risk his career by proposing such a theory? From a physics perspective, parallel universes are a captivating but challenging concept to test. It first emerged in the realm of quantum physics, which is known for its unpredictability, even when you have all the information about a system. For instance, if you shoot a single electron through a double slit, you can only predict the probabilities of where it might land. You can't precisely pinpoint its location. One intriguing idea, called the many worlds interpretation of quantum mechanics, suggests that all possible outcomes happen, but each outcome occurs in a separate universe. Exploring all these possibilities requires an infinite number of parallel universes. We'll delve deeper into this concept later in the video. For now, let's continue. Another way that the idea of parallel universes enters physics is through the concept of the multiverse. Our observable universe came into existence 13.8 billion years ago with the hot Big Bang, but the Big Bang itself wasn't the absolute beginning. Before that, there was a very different phase in the universe that set the stage for and led to the Big Bang. This is known as cosmological inflation. The key point is that inflation doesn't come to an end everywhere simultaneously. In some regions, it continues. Where inflation persists, it generates more space and the potential for additional Big Bangs. Once inflation begins, it's exceedingly challenging to halt it completely. As time progresses, more and more Big Bangs happen, entirely separate from one another. This results in an immense number of independent universes, creating what we call a multiverse. Some researchers propose that at the opposite end of the Big Bang's timeline, tracing back in time, there might have existed a universe that was a mirror image of our own. Here's an artist's depiction of the universe's history as portrayed by the Wilkinson Microwave Anisotropy Probe, WMAP, which spent 9 years creating maps of the cosmic microwave background, shedding light on events about 375,000 years after the Big Bang, before stars and galaxies formed. In a relatively recent addition to multiverse theories, scientists from the Perimeter Institute for Theoretical Physics in Waterloo, Ontario, suggest that the universe started with the Big Bang. On the flip side of the Big Bang's timeline, stretching back in time, they propose a universe that was the exact mirror image of ours. Rather than stating that there was a different universe before the Big Bang, this idea suggests that the universe before the Bang is, in some sense, a reflection of the universe after the Bang. In this scenario, everything, from particles like protons and electrons to everyday actions like cracking an egg, would be reversed. Antiprotons and positively charged electrons would form atoms, and cracked eggs would uncrack and go back into chickens. Eventually, this universe would contract to a singularity before expanding into our universe. Another way to view it is that both universes came into existence at the Big Bang and expanded in both directions in time simultaneously. The significant challenge for both of these concepts is the lack of a way to test or confirm the existence of these parallel universes. If we're confined to our universe, how could we ever access another one? Our laws of physics dictate that certain quantities are always conserved, and particles can only interact with other particles of matter and energy according to these laws. In all our experiments, observations, and measurements, we've never found evidence that necessitates the existence of parallel universes. If this notion were true, it would be groundbreaking. It would indicate that our current understanding of the universe is incomplete, and there's much more waiting to be discovered than we ever imagined. These other universes wouldn't just exist. Matter and energy from them might be able to cross into our universe and interact with our matter and energy. If this were the case, some of our most extravagant science fiction ideas might become possible. Quickly, physicists delving into the quantum realm discovered some strange phenomena. On this tiny scale, particles seem to transform in unpredictable ways. For instance, scientists have observed photons, those minuscule packets of light, behaving both like particles and waves. Even a single photon can do this shape-shifting. Think of it this way. Imagine if you looked and behaved like a solid person when a friend saw you, but then, when he glanced back, you'd become like a gaseous form. This is a simplified version of the Heisenberg uncertainty principle. Physicist Werner Heisenberg proposed that merely observing quantum matter influences how it behaves. As a result, we can never be entirely certain about the nature of a quantum object, such as its speed and position. This brings us to another idea about parallel universes known as the Copenhagen interpretation of quantum mechanics. Proposed by Danish physicist Niels Bohr, this interpretation suggests that quantum particles don't exist in just one state. They exist in all of their possible states simultaneously. The sum of these potential states for a quantum object is called the wave function, and the condition of an object being in all its possible states at once is referred to as superposition. Bohr's theory states that when we observe a quantum object, we affect its behavior. Our observation disrupts the object's superposition, compelling it to select one state from its wave function. This concept explains why physicists can obtain different measurements from the same quantum object. It chooses different states during various measurements. Young Hugh Everett largely agreed with the ideas put forth by the respected physicist Niels Bohr regarding the quantum world. He accepted the concept of superposition and the notion of wave functions. However, Everett held a fundamental disagreement with Bohr. According to Everett, measuring a quantum object doesn't force it into one definite state. Instead, it leads to the universe splitting. The universe duplicates itself, creating one universe for each possible outcome of the measurement. For instance, if an object's wave function indicates it can be both a particle and a wave, when a physicist measures it as a particle, the universe splits into two separate universes. In one, the scientist measures the object as a wave, and in the other, as a particle. This also explains how a single particle can be measured in multiple states. As unsettling as it may sound, Everett's many worlds interpretation has implications beyond the quantum level. If an action has more than one possible outcome, then, according to Everett's theory, the universe splits when that action occurs. This splitting even happens when someone chooses not to take an action. This means that if you've ever been in a situation where death was a possible outcome, then, in a parallel universe to ours, you didn't survive. This is one of the reasons why some find the many worlds interpretation disconcerting. Another disconcerting aspect of the many worlds interpretation is how it challenges our linear concept of time. Imagine a timeline depicting the history of the Vietnam War. Instead of a straightforward line showing the progression of significant events, a many worlds timeline would depict every potential outcome of each action taken. Further, It would document each potential outcome of the subsequent actions resulting from the initial outcome, creating what seems like an infinite number of alternate universes. However, individuals cannot be conscious of their other selves or even their deaths in parallel universes. So how could we ever determine if the many worlds theory is accurate? The notion that the interpretation is theoretically possible gained traction in the late 1990s with a thought experiment known as quantum suicide. This thought experiment, used to theoretically prove or disprove an idea, renewed interest in Everett's theory, which was initially met with skepticism. As the possibility of many worlds became more apparent, physicists and mathematicians have endeavored to delve deeper into the implications of this theory. However, it's worth noting that the many worlds interpretation is not the sole theory seeking to explain the universe, nor is it the only one proposing the existence of parallel universes. So, do parallel universes truly exist? According to the many worlds theory, we can't be entirely certain, as our awareness of them is limited. String theory, though tested negatively at least once, is another contender, with Dr. Kaku among its proponents. However, Einstein did not live long enough to see others take up his quest for the theory of everything. Yet, if the many worlds theory is correct, Einstein may still be alive in a parallel universe, where physicists may have already discovered the elusive theory. But then, how can we test the existence of parallel universes? Well, if our universe collided with another, it would offer some evidence. Some theorists have suggested that colliding universes could leave cold spots or hot spots on the cosmic microwave background, CMB, the afterglow of the Big Bang. If so, we should be able to detect those spots with advanced sky surveys. Gravitational waves, which are ripples in the fabric of space-time, might also provide evidence to support the theory of cosmic inflation. The theory predicts that gravitational waves left over from the Big Bang could put tiny curls into the CMB, which some telescopes are actively searching for today. If researchers can spot such curls in the CMB as they thought they did back in 2014, it could ultimately boost support for the idea that there's another you out there going about their daily life in an alternate universe, proving sci-fi writers correct once again. However, before that happens, there is a connection between parallel universes and two other mysterious and scary space phenomena: black holes and white holes. Black holes are those terrifying objects in deep space that swallow everything that comes near them. They are formed when giant stars collapse on themselves, creating very dense masses that have gravitational forces so strong that nothing can escape from their attraction, not even light. White holes are the opposite of black holes because they push out everything inside them, and nothing can go inside. There are various theories about the formation of white holes, which we won't go into in this video. But how are the three connected? In essence, every white hole could generate other Big Bangs, generating multiple universes inside our own or outside its radius or boundaries. Hence, the laws of physics there would be different. Reality could be made from antimatter, or possibly time wouldn't be positive and unidirectional. Probably these universes would be mirrors of our universe, with divergent timelines based on different quantum states coming to life, confirming quantum superposition. Let's hear what you think of parallel universes in the comments section below. The Antarctic Impulsive Transient Antenna Experiment, ANITA, is a balloon-borne experiment designed to detect radio waves. Recently, it picked up radio waves with specific energy and directions originating from beneath the Antarctic ice, which is precisely what the experiment was meant to do. In the cosmos, various types of high-energy particles, including elusive neutrinos, travel through space. While some neutrinos come from sources like the Sun, stars, or the Big Bang, others are produced by incredibly energetic astrophysical phenomena like pulsars, black holes, or mysterious unidentified objects. These high-energy neutrinos have a range of energies, with the most energetic ones being the rarest and most intriguing to many physicists. Neutrinos are challenging to detect because they mostly pass through normal matter without interaction. It would take an expanse of about a light-year's worth of lead to have a 50 chance of stopping one, and consequently, they can arrive from any direction. However, Most high-energy neutrinos that we observe are produced when other cosmic particles collide with Earth's upper atmosphere, resulting in cascades of particles, some of which transform into neutrinos. These neutrinos often traverse the Earth with minimal interaction, only engaging with the Earth's outermost layers. Some of these interactions produce signals that our detectors can pick up. There's compelling evidence against the idea that these high-energy neutrinos are regularly passing through the Earth and Antarctic ice. The ice cube neutrino detector, for instance, has not observed such signals, despite its sensitivity to high-energy tau neutrinos. When Anita detected radio signals it couldn't explain, the leading hypothesis was that high-energy tau neutrinos were traveling upwards through the Earth. However, observations from the ice cube detector contradict this hypothesis, suggesting that there's no astrophysical source generating the particles detected by Anita. So, where do parallel universes enter the picture? Anita's observations left only three possible explanations: an astrophysical source for these particles, a detector flaw or misinterpretation, or something extraordinarily exotic and beyond the standard model known as CPT violation. Further investigations have ruled out the first option, making the second option the most likely. The third option, which suggests that our universe cannot violate CPT, implies that these observations come from a parallel universe where CPT is reversed. However, this explanation is considered highly unlikely and poorly substantiated. In the realm of science, conventional explanations that don't involve new physics must always be eliminated before considering groundbreaking ideas. Over the past decade, numerous remarkable claims have crumbled under scrutiny, emphasizing the importance of rigorous scientific investigation. For example, neutrinos do not travel faster than light, dark matter and sterile neutrinos remain elusive, cold fusion isn't viable, and the concept of an impossible reactionless engine has failed. The many-worlds theory and the Copenhagen interpretation are not the sole contenders in the quest to explain the fundamental nature of the universe. Quantum mechanics isn't the only branch of physics seeking such an explanation, and theories in the realm of subatomic physics remain just that: theories. This has led to divisions in the field, much like the differing psychological frameworks proposed by figures such as Carl Jung, Albert Ellis, and Sigmund Freud. Physicists have been working on what might be called reverse engineering the universe. They have studied the observable universe and worked their way backwards to probe the smallest levels of the physical world, aiming to reach the most fundamental level that will provide a foundation for understanding everything else. Following his groundbreaking theory of relativity, Albert Einstein spent the remainder of his life in pursuit of the ultimate theory that would answer all physical questions. This elusive theory is often referred to as the theory of everything. Quantum physicists believe they are on the path to discovering this final theory, but another branch of physics contends that the quantum level is not the smallest, and therefore cannot yield the theory of everything. These physicists turn to a theoretical subquantum level known as string theory for answers. String theory, conceived by Japanese-American physicist Michio Kaku, posits that the fundamental building blocks of all matter and the physical forces in the universe, including gravity, exist at a subquantum level. These building blocks resemble tiny strings, similar to rubber bands, which constitute quarks, quantum particles, and subsequently, electrons, atoms, cells, and more. The behavior of this matter depends on the vibrations of these strings, forming the basis of our entire universe. String theory goes further to propose that our universe is composed of 11 separate dimensions. Like the many-worlds theory, string theory suggests the existence of parallel universes. According to this theory, our universe is akin to a bubble coexisting with similar parallel universes. Unlike the many-worlds theory, string theory posits that these universes can interact with one another. It suggests that gravity can flow between these parallel universes, leading to occurrences like a Big Bang, similar to the one that gave rise to our universe when these universes interact. While physicists have developed instruments capable of detecting quantum matter, the subquantum strings remain theoretical and have yet to be observed. String theory's status as a theoretical framework has led to criticism, but it still has proponents who believe it holds validity. However, Einstein did not live long enough to see others take up his quest for the theory of everything. Yet, if the many worlds theory is correct, Einstein may still be alive in a parallel universe, where physicists may have already discovered the elusive theory. And that concludes this video. If you enjoyed it, please leave a like and subscribe to the channel for more content. Goodbye, and I'll see you in the upcoming video.